Hello class, and thank you for watching. In topic 2.4, exponential functions manipulations, you're going to apply the properties of exponents to write horizontal transformations of exponential functions to evaluate these type of exponential functions. Now we're going to be focusing on, again, horizontal translations, horizontal stretches and shrinks, and of course, reflections, horizontal reflections, which is this one right here, okay? Now, let's recall again that a horizontal translation is going to shift the graph again to the left and to the right. If I'm subtracting a value of h, we'll call it h, then that's going to shift this function b of x to the right by h units. Now, if I'm adding that number of h, it just simply moves it to the left direction. Now, compare that to vertical translations, adding again a value or subtracting a value, we'll call it k, to the entire function itself, notice a different notation, that's going to shift the graph upwards or downwards. Now, these type of graphs, if you recall from the previous video, have horizontal isotopes, and the horizontal isotope is also going to shift accordingly. Instead of being at 0, adding again this value of k will shift the horizontal isotope to k units, and subtracting the k will shift the horizontal isotope to y equals to negative k. Now, in the previous example, we talked about vertical reflections and how that graph is going to look like. The same thing with horizontal reflections. And we're going to talk about, again, how we can graph and how we can manipulate a horizontal reflection using, again, exponential properties. And just to finish the recap right here, vertical stretches is a result of multiplying the scalar to b to the x, which is, again, just the general form of writing an exponential function where the value of a is essentially our y-intercept. Okay, if the value of a is a number bigger than 1, then it's going to result in vertical stretch, but if it's a number less than 1, still positive, then it's going to result in a vertical shrink. And then finally, we have our horizontal stretches and shrinks. Now, a horizontal stretch and shrinks, again, just like with our horizontal translation, this c, again, is going to result in the opposite thing. If the value of c is a number between 0 and 1, then it's going to stretch. And if it's a number greater than 1, then it's going to be a horizontal shrink. Our horizontal dilation, shrink or stretch, is the result of multiplying by the reciprocal of whatever our scalar c is. Now, let's determine again the horizontal transformation of each of the following exponentials and see how that's affecting the graph. Well, right here, this right here, f of x is equal to 4 to the x plus 2 power, will give us the same graph. Will give us the same graph as of y equals 4 to the x. But the only difference is that the plus 2 is going to shift the graph of y equals 4x 2 units to the left. And how does this one compare? So how does that compare to letter B? Well, letter B, g equals to 2 to the 3x. That's going to have the same graph as y is equal to 2 to the x. But the 3x is going to result in a horizontal dilation by a scale factor of half. Well, I should really be specific, and it'd be a horizontal shrink by a factor of half. Not half, I'm sorry, a third. That's a 3. So 1 over 3 by the reciprocal of that. Well, let's look at the next example. For the next example, let's describe this transformation, excuse me. So this graph, H, h is going to have the same graph as y equals 9 to the x. But how is this going to change the graph? Well, it's going to be another horizontal dilation. But 9 divided by x is the same thing. I'm sorry, x divided by 2 is the same thing as saying 1/2 times x. So this graph of 9 to the x power is going to be, oh, I'm sorry, h of x is going to be the same as y equals 9 to the x, but it's going to be horizontally stretched by a factor of, well, the reciprocal 1/2 is 2. Now let's look at example D. Well, for example D, k of x is going to have the same graph. Sorry, my handwriting is horrible right now. The same graph as y equals to 5 to the x. And the minus 1 here that we're performing again to the x is going to translate 1 unit to the right. Since it's subtracting 1, it's going to move it to the right. It's going to shift it 1 unit to the right. Okay, now let's look at the next page and let's review again. Let's look at these horizontal transformations and how they correlate again to exponent rules. Well, one of the exponent rules I want to focus on right now is the product property. Recall from Algebra 1, Algebra 2, that the product property states that if we're multiplying two powers, like b to the m power times b to the n power, we can simplify this as b to the m plus n power. Then we're going to end up again adding those exponents together. Now, this rule is very simple to explain because we know that a power simply identifies the number of factors that we have. So like if I have x to the third power, that means x times x times x. I'm multiplying 3 factors of x. Similarly, x to the second power means x times x. So here, this is going to end up equaling to x plus 3 plus 2, which is x to the fifth power, which makes sense because if we look at the number of factors that we have, x to the third, like I said, is x times x times x, and x squared is x times x. The number of x's that we're multiplying here is going to be a total of 5. 1, 2, 3, 4, 5. So we end up with x to the fifth power. That's why this rule is equivalent to this. Now, the key thing in understanding this is that we can use this rule again, that this is biconditional. Having this, or having x to the fifth, which is this, can also go backwards. We can write that. So using this property from right to left, we can break up an exponential situation. Using this property, we can break up this situation where we have 2 to the x plus 5 power as 2 to the x times 2 to the fifth power. Since these quantities, exponents are being added together, that means I'm multiplying two powers, where one power of base 2 is raised to the x power, and another power of base 2 is raised to the fifth power. And I can simplify this since I know that 2 to the fifth power equals to 32. I can rewrite this as 32 times 2 to the x power. Let's now look at the power property. The power property states that if I have a power raised to another power, right here, this gets simplified by multiplying the inner exponent of 2 with the outer exponent of n. For example, x to the third to the second is equal to x to the third times 2, which is x to the sixth power. Well, let's explain this in further. So x to the third to the second means I have an x to the third times an x to the third, 2 of those. So this outer exponent means I have 2 of what's inside the parentheses. Now we know again from exponent rules that x to the third means I'm multiplying 3 factors of x, and the same thing on the other one, 3 factors of x. So here, since I'm multiplying 3 here and multiplying 3 more there, I am multiplying a total of 6. So as you see right there, I'm just doing 3 times 2, which is equal to that. Now, the cool thing about this is that I can use this again backwards. This is, again, a biconditional statement, that if it's true to get this, to get that, I can use this answer to go back to what I originally started off with. So for example, right here, I have 2 to the 3 times x power. Well, since I'm multiplying these exponents together, 3 to the x, well, this means, again, 2 to the 3 times x. That means I could rewrite this as 2 to the third power and the x power outside, which can be simplified as 2 to the third, which is equal to 8, to the x power. So I can use this rule backwards and go from here to there, which then lets me simplify this part right there. Now let's go over the last rule. The last rule is the negative exponent rule. The negative exponent rule states that if I have a negative exponent, like right here, all I have to do is simply get the reciprocal of this, so 1 over b. This doesn't necessarily mean put everything under 1, just simply flip it. This is notation for reciprocal, and that's going to change the exponent from a negative number to a positive number, to a positive exponent there. So for example, this right here, this is 1 over x to the third power. Now this is a little bit more harder to try to explain and then go into detail like we did in the previous one, so I'm not going to go there. We just need to understand this one just like that. So we have 1 over x, and that changes the exponent to a positive 3. And I could write it like this in that notation, or I can write it in this notation like that. They both mean the same thing, okay? The more common one is this one right here. So let's now look at how this applies. So right here, this can be written as 1 over 2, and that changes the exponent to positive 3, which we can then write as 1 over 8, since 1 is going to be raised to the third power, that's going to be 1, but 2 raised to the third power, that's still going to be 8, since 2 times 2 times 2 does in fact equal to 8. So that's how we simplify that. Now let's use these properties again to re-examine the exponential function from example 1a and see if we can use our exponential properties to rearrange the function into an equivalent form. Well, example 4a was that, again, this one right here, f of x, let me rewrite it, f of x is equal to 4 to the x plus 2 power. Well, we can apply the power property, this one right here, the product property, I'm sorry, not the power property, the product property, to show that 4 to the x plus 2 is equivalent to 4 to the x plus, times 4 to the second power. Since these exponents are added together by the product property, that means that we have a base of 4 raised to the power of x times another base 4 raised to the power of 2. And because of this separation, being able to separate this, we can rewrite this portion and rewrite this function of f of x as 16 times 4 to the x power. And therefore, we can rewrite the function f of x as f of x is equal to 16 times 4 to the x power. Now, if you notice again on the previous examples, not just this one, but on these examples as well, every horizontal translation of an exponential function is equivalent to a vertical dilation of that same exponential function. So we go from sliding things left and right to being able to write a function as a vertical dilation, as a vertical stretch or shrink of that exact same function. So let's apply this and let's practice some more problems to this using this rule right here. Well, each of the following exponential functions has a horizontal translation for each write an equivalent representation of the vertical dilation and no horizontal translation. So let's do that right here on this example. So here we have f of x is equal to 2 to the x plus 3 power. So 2 to the x plus 3 power. Well, by the product property, since we're adding these exponents up here, x is being added with 3, that means we can write this as 2 to the x power times a 2 to the third power. And since 2 to the third power can be simplified to 8, that means we can write f of x as the product of 8 times 2 to the x power, or 8 times 2 to the x power, like this. Without parentheses, it will look like this. With the parentheses, the exponent would be on the outside. The x, again, 2 to the x power, like that. So this is just a way of, again, manipulating our function and writing our function from having shifted 2 to the x 3 units to the right, having to now look as a vertical dilation of a scale factor of 8. Okay, so now for example B. Well, first of all, let's recall that k of x is going to shift y equals 4 times 3 to the x power 2 units to the right. So now let's rewrite this from this horizontal shift to just a simple vertical dilation. Well, 3 to the x minus 2, let's focus on this right there. This right there means that we have 3 to the x multiplied with 3 to the negative 2 power. Okay. Well, having 3 to the negative 2 power using our negative exponent rule simply means that if I get the reciprocal of 3, so 1 over 3, that changes the exponent from a negative 2 to a positive 2. And we can simplify this. So we have 4, 3 to the x, and then 1/3 to the second power is 1 over 9, since 1 over 3 times 1 over 3 is 1 over 9. So that means that k of x can be written as 4 over 9 by multiplying, again, this quantity with this quantity. That's 4 over 9 times our exponent of 3 to the x power. Or you can write it like this, 4 over 9 times 3 to the x power if you don't want to write the parentheses. They're both equivalent. You just have to make sure, again, to indicate that you're multiplying those quantities by putting a times symbol in between. I normally just stick with the parentheses, okay? I like using the parentheses better. But it's up to you how you want to write it. But those two things are going to be equivalent. Let's now move on to the next page now. Now, we can also use the power property of exponents to show that every horizontal dilation of an exponential function is equivalent to the change is equivalent to changing the base of the exponential function. So, as you see right here. Now, the key thing again, well, before we go on, let's review what a rational exponent does and what a fraction is as an exponent. So let's say we have a base, we'll call it b, base b, okay, thicker marker, base b, and we're raising it to a rational function, n over p, okay? If my exponent is a fraction, a rational number, this is equivalent to getting this base, raising it to the power of n, And this denominator in this exponent is the index to the root of b. This again is referred to as the rational exponent property, where again p is not going to end up equaling to 0, okay? And it's going to actually be greater than 2. P has to be greater than or equal to 2. Okay, it cannot be less than 2. It has to be greater than or equal to 2. So for example, okay, 16 to the 1/2, well, that's the same thing as using, since this in the denominator is 2, that means we have an index of 2, and we have the root index of 2 of 16, which normally is just written as the square root of 16. When our index is 2, we don't write the number 2 out there, okay? We just simply ignore it, and it's understood to be 2. 16 is raised to the first power, and well, since it's raised to the first power, we don't have to write that number 1 out there or in there, and we could just write it as 16. And well, the square root of 16 equals 4. Same thing is true with the next example. If I a to the 1/3 power, our index is going to be 3. So we have the third root of 8 to the power of 1. So to this power of 1, and since the power of 8 is 1, we don't have to write that power of 1, is understood to be 1. And well, this simplifies to the number 2, since the third root of 8 is 2. And how do I know that? Because again, working backwards, I know that 2 to the third power is 2 times 2 times 2, which equals to 8. So that would mean that the third root of 8 would be 2. Now that we've reviewed again that property, each of the following exponential functions has its horizontal dilation. Let's write each equivalent representation for each that changes the base of the exponential function. So let's start with example A. So here, by the power property, 9 to the 2x is the same thing as 9 to the second power and then raised to the x power. And since 9 to the second power means 9 times 9, which is 81, I can write 9 to the 2x power as 81 to the x power. So these two things are equivalent. This is the same thing as that. Let's now look at this example right here. We have 9 and 16, and only 16 is being raised to the x over 2 power, which is the same thing as 1/2 times x. Well, by the power property, 16 can be raised to the 1/2 power and then to the x power as such. And since taking 1/2 is the same thing as taking the square root, I can write this, and I'm going to take a note of this, okay? 16 to the 1/2 is the same thing as taking the square root of 16, which is equal to 4. I can write this here as 4 and then raised to the power of x. So f of x is equivalent to 9 times 4 to the x power. Let's look at example C. So example C, similar situation. We have g of x is equal to 3 times 4 to the x power. So we can think about it like this, which means 4 to the x power means 4 is raised to the second power and then raised to the x power. And since 4 to the second power is 16, 16 is being raised to the x power. Now, I didn't emphasize this on the last example, but these things cannot be multiplied together because 16 is being raised to the x power. And by the order of operation, I would first have to raise 16 to the power of x before I can multiply this with 3. So g of x is equivalent to 3 times 16 to the x power. So by doing and using this property, I am changing the common ratio to this thing and changing the horizontal dilation of a scale factor of 1/2 by changing the common ratio to 16 instead of the base of 4. So for letter D, same situation here. We have 4 and 9 to the x over 2 power. That's the same thing as 9 to the 1/2 times x power, which means 9 is being raised to the 1/2 power and then multiplied by x. Well, again, like the previous example, raising 9 to the 1/2 power is the same thing as taking the square root of 9, which equals 3. So I can rewrite g of x as 4 times 3 to the power of x. Okay, now let's look at an example. We're going to use double properties. Okay, the product and the power, and we're even going to use the negative exponent rule. So here, let's first start off by writing this as 4 to the 2x times 4 to the negative 3 power. Since I am subtracting these exponents, that is the same thing as adding, again, a negative 3. So using the product property, where these exponents are added together, that means I have a power of base 4 to the 2x times a power of base 4 to the negative 3 power. Now, 4 to the 2x, that can be written as 4 to the 2 and then raised to the x power times 4 to the negative 3. Well, that's the equivalency of getting the reciprocal for 1 over 4, and that changes the exponent to positive 3. Well, 4 to the second is 16. So 16 can be raised to the x power, and 1 over 4 to the third power means 1 over 4 times 1 over 4 times 1 over 4, which is going to be 1, since 1 times 1 times 1 is 1, and 4 to the third power, 4 times 4 times 4, that's equal to 64. Now, again, these things cannot be multiplied together, and I cannot simplify this because the order operation requires me to get 16 and raise it to the power of x before I can multiply with 1 over 64. So that means that f of x is going to be equivalent to 1 over 64 times 16 to the x power. And now for example f. So h of x is equal to 27 to the x over 3 plus 1 power. So let's first do this. First, let's write 27. X over 3 is the same thing as 1 over 3x plus 1. Well, by the product property, again, since these values are being added together, I can separate this and write this as a base of a power with base 27 to the x plus 1 power. And then I can write and multiply another power of the same base 27 raised to the first power. Well, 27 to the 1/3 power is the same thing as 27 to the 1/3 to the x power. So all I've done is write this as that. And now times, well, 27 to the first, that just simply is 27. Now, 27 to the 1/3 power, that's the same thing as taking the third root of 27, okay? And to figure this out without the use of the calculator, well, I just need to know what number can I multiply by itself 3 times to get 27. And that number would have to be 3. 3 times 3 times 3 is equal to 9. And 9 times 3 equals 27. So that means that if I take the third root of 3, the third root of 27, that has to equal to 3. Since 3 to the third power equals 27, going backwards, that would be again this. So I have 27, I have 3. I have 3 to the power of x times 27, which again is h of x. And if I just rearrange this, I can put the 27 in the front and 3 to the x power in the back. And this is what the transformation will look like, where 27 is a y-intercept and my ratio, my common ratio base is 3. Okay, well, this concludes our notes for topic 2.4, exponential function manipulation. Thank you again for watching. If you have any questions, send me a message through email or through Parent Square. And like I always say, I appreciate you watching and I hope you have a great day. Goodbye.